today's lecture on Physics 2. Today we will be discussing about Gauss's law, specifically about uniformly charged electric sphere. Okay, so as you know, in this picture you can determine that the electric field's intensity due to the uniformly charged spherical shell, where theta is the angle between the direction of E and a small area. Okay, so what will we learn about today? Today we will learn about Gauss's law and the electric flux, and finally the application of Gauss's law on uniformly charged electric sphere. Okay, furthermore we have a special guest today in class, which will be John Carl Friedrich Gauss.
Everyone's wondering who's Johann Carl Friedrich Gauss. It's me, Johann. I'm a scientist who has contributed in astronomy, mathematics and physics. I was born in 1777 and passed away in 1855 at the age of 77. Somehow I had to come back to life to tell you face to face what I have discovered in my whole life with the magnetism and electricity by deriving important laws. I have changed the world by my laws, law of magnetism and law of charge. Back in 1780s, Faraday and I went to a coffee shop to grab coffee and discuss few equations. The scientist Ampere, who came with the idea of the circuit law, joined us in working out and set up the equations together. So once we have combined everything together, you guys would be able to have enough knowledge to work out together the uniformly charged solid sphere non-conducting of radius by using our laws.
Alright, thank you Gauss for your wonderful speech. Moving on. Now we will be discussing about Maxwell's equations for classical electrodynamics. Okay, as you can see here, we have Gauss's law for magnetism, Faraday's law of induction, and Ampere's law. You can see that we have both of the laws in differential form and integral form. Okay, so moving on. What is electric flux? Electric flux refers to the electric field lines that penetrate a given surface. For a given uniform electric field E passing through an area A, the electric flux is identified as the electric flux equals to E times A times cos theta. Okay, what is Gauss's law? Gauss's law is known to be the electric flux equal to the enclosed charge divided by the permittivity of space, which is known to be N0 rule. What is a Gaussian surface? A Gaussian surface is known to be a closed surface that divides space into distinct inside and outside regions. The electric field must be perpendicular to the surface and same magnitude at each point. We have two figures here, the appropriate Gaussian surface and the inappropriate Gaussian surface. As you can see in the appropriate Gaussian surface, figure A is a cubic Gaussian surface. The field is going into each phase of the box. There must be a negative charge in the box. As for the inappropriate Gaussian surface, a Gaussian surface that does not match the symmetry of the electric field isn't very useful. What is epsilon naught? This is the symbol for the epsilon naught and refers to the permittivity of free space, which is known to be the constant of 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. What is charge? So we know that charge is divided into two parts, the positive charge and the negative charge. And it is known that charges have electric field lines. For example, the positive has an outward going electric field line which attracts the negative charge, which has the inward electric field lines. So electric field lines, or electric charge, is the physical property of matter that causes it to experience a force when placed in an electromagnetic field. Further on, what is an electric field? An electric field is E at any point in space is defined as the force exerted on a tiny positive test charge placed at the point divided by magnitude of the test charge Q, which is E equals to the force F divided by the charge Q.
Alright, now let's look onto the application of Gauss's law. We're looking at the moment on the uniformly charged solid sphere, which is non-conducting. of radius r. As we know, if it's a non-conducting sphere, that means all the charged particles are distributed all around the sphere. So for the case 1, when r is smaller than capital R, which is inside, as you can see on the figure of Gaussian surface, the total electric flux we're going to get would be the integration of E dot dA, a small area, equals to charge divided by epsilon naught. As we can see from the figure, E and dA are parallel to each other on a Gaussian surface, which give us the angle of 0 degree. And as we know, cos 0 equals to 1, we can substitute that cos theta in the formula, and we can get integration E dot dA equals to Q by epsilon naught. While in the Gaussian surface of area 1, we can know that E is a constant everywhere because of the same radius. We can get E out of the integration part, and we know if we start integrating all the small area, we will find out the whole area of the sphere, which we can represent as a 4 pi r square, equals to, as we know, Q is the charge of, we need the Q charge of the Gaussian surface, not of the whole sphere, because it's inside. So to get that one, we need to have divided volume of Gaussian surface divided by the volume of whole sphere, which is 4 by 3 pi r square cube divided by 4 by 3 pi capital R cube, which gonna give us the formula E equals to Q by 4 pi epsilon naught into small r divided by R cube, which shows us that electric strength is directly proportional to the small r, which is the Gaussian surface radius. So as you can see on the figure, the more radius, bigger the radius, bigger the electric strength. Alright, now let's look onto the case 2, when small r is greater than capital R, which is outside the sphere. Same electric flux, we can use same formula, integration of E dot dA equals to Q by epsilon naught. As we know, on this one too, E and dA are parallel to each other on the Gaussian surface, which makes the angle of 0 degree, and which comes to cos theta equals to 1. By substituting that cos theta equals to 1 on the formula, we can get E dot dA equals to Q by epsilon naught. As we know, E is a constant on Gaussian surface, on this case too, due to the symmetry of the charge distribution. We can take E outside of the integration and we can leave it dA. And also, as we were talking about before, that a small area, if we start doing addition, which is the integration, we can find the area of the sphere, which is 4 pi r square. If we place 4 pi r square on the bottom of r square, we can find this formula, which gives us E equals to kcq by r square, which is the final product, where kc is the Coulomb's constant, which has a value of 8.99 into 10 to the power 9. And also, this formula shows that E is inversely proportional to the r square, where r square is the Gaussian surface radius. So from this graph, you can see the more the radius, the lesser the electric field is strength. That's all for today.